All right, looks like we are live. Let me know if you can't hear me. So my name is Armin Oganesian. So I'm on the governing body for STAN. I'm also an assistant professor of biostatistics at Brown University. So I'm really excited to get this event kicked off. So I just wanted to say a few words about StanConnect. So StanConnect is really this series of virtual sessions or mini symposia that's being held throughout this year in lieu of StanCon. So there are some issues setting up StanCon due to the pandemic, but we think that this is an exciting sort of way to do things a little different this year. So this is truly like a very bottom-up endeavor. We issued a public call for session proposals, and one of these sessions on simulation-based calibration on SBC was proposed, and so we're really grateful to the session organizers, and we're looking forward to these sessions. Are very excited, and we would love all of your feedback at the end as well. If you liked it, if you didn't like it. I'll also post a link to a donate link. So this is all completely free, but we would appreciate any donations to the STAN project. So I'll put that in the chat. And so feel free to take a look at that. Otherwise, I'll pass it along to, I think, Hyunji, who will take over the rest of the talk. Thank you so much for organizing, and thanks everyone for turning out. This is a really great turnout. I think we have almost 60 people in attendance. All right, everyone, bye and enjoy.
Bye-bye. Hello, everyone. My name is Hyunji Moon. I'm an organizer of this conference. And yeah, to start with, I'm a Bayesian enthusiast. A random alphabet B that's at the end of my Twitter ID stands for Bayesian. And two things drew me into Bayes. The first was the ability to simulate, and second was a gradual update. Somehow, SBC contains both. With the generative structure of our own design, we can eliminate models that are inconsistent and therefore bootstrap. It's like a magic 8-ball. Which gives 20 possible answers, 10 being affirmative, 5 being non-committal, and 5 being negative. The only difference is, for SBC, you should really be paying attention to those 5 negative answers. Timo will give great tips for that. With SBC, you can verify all possible imaginable assumptions, including model assumptions, and the decision, which is Daniel's talk is about. However, with great power comes great responsibility. SBC's computation is very expensive. And that is why we should really be knowing about its component. One would be the prior, which is Paul will kindly introduce to us. And another is posterior sampling, which is Louis' talk is about. All in all, enjoy. And also, lastly, Martin, Shin, and Timu, we have like StanCon staff. We have put great efforts into developing packages and designing tutorials for the past few months. Thank you all. It was a great journey. I'll now toss to Martin, who will introduce SBC briefly. Thanks, everyone.
Okay, hi everybody. So we were supposed to have Andrew Gelman to do this intro, but something didn't work out. So I'm gonna be filling in for Andrew, just to give a brief overview of what SBC is for those who haven't used it before, and how it relates to model validation and what it can and cannot do for us. Just this is my sponsor, so I have to show this at every presentation. Sorry for annoying you. Anyway, so in a full model workflow, we usually start with prior predictive checks that let us check that our prior is sensible. We may want to validate computation for our model. We may want to evaluate our model fit to real data with things like posterior predictive checks, but there are also other tools to do this. And then we want to use the model for something actually useful. And SBC lives where in the space for validating computation. It is a tool to validate that our model does what we believe it does. So it is a tool to check that you implemented your model correctly. And it's just one of tools to validate your model. And it has the advantage is that because it's a simulation-based tool, SBC can be run even before you collect data. So you can use it to validate that your model actually works and sensible and doesn't take 20 hours before you even collect the data. There's going to be a tutorial that will hopefully show you how to use it. And it's important to remember that there are two types of problems that you can have with the STAN model. So one of them is you have a bug in your model. It doesn't do what you believe it should do. And another type of problem is there's a mismatch between the data you collected and your model. And SBC will focus only on bugs in your model. Since it's based on simulated data, there's no way it could help you with data model mismatch. So you'll have to use other tools to check for this. And how do we separate a bug in a model from a mismatch, from a complete mismatch with the data? And if we simulate the data exactly as the model assumes, then any problem has to be a bug. So we remove part of the uncertainty by completely controlling our data. So we can remove some of the uncertainty, and we can be sure that the problems that remain are problems in the model and not problems with the data, because we control the data. So what does it mean to simulate exactly as the model expects? Yeah. So there's just like very quick example with STAN and R, so that we have exactly the same priors. We draw A from a normal distribution with mean 5 and SD3, and that's our prior in our STAN code. Now we do order for the parameter. We compute our mu. Now this is a simple linear regression. We compute our mu, and we compute our mu the same way in the STAN model. So we would expect, if everything works well, that once we run this STAN model, we're going to recover the parameters we simulated here, because it is exactly the same process. And so how do you spot a failure when you have a simulated data set and a result? So like if we see that our posterior interval is from 0.007 to 0.07, so like how can we tell if this is a problem? So is this a problem if we simulated alpha as 0.3? Well, probably not. So it's like just like somewhere in the middle of the interval. So it's probably not a problem. So if alpha is 0.007, like is that a problem? Like maybe not. Like it's outside of the central 90% interval, but is it a big deal? Is that a problem? Well, maybe if alpha is like -30, then we can be certain. Yeah, that looks like a problem. And so that's a situation where we see just from a single simulated data set that we have a problem. But more frequently, our results are going to be like somewhat congruent and we will need multiple simulations to aggregate information. So maybe if all the time our simulated values are exactly recovered just in the middle of the posterior distribution, that's also suspicious. We expect like 5% of the cases to be extreme, and so usually we need more than one simulation. But we also have STAN diagnostics. So if like STAN tells us that we have 1,000 divergent transition, we can be quite sure there's a problem. Yeah. We also like with this, just looking at a single simulation, we cannot like spot success. Like what does it mean for the model to work well? And this gets us to the core consistency requirement for SBC, and that is that for 95% of simulations, the true parameter lies within the center 95% credible interval. Or more generally, for any x, in x% of simulations, the true parameter lies within the x% posterior credible interval. Yeah. And this intuition that we of consistency works in SBC just that we have the posterior for a single fit, we get independent samples, and for each simulation we take the rank of the true value within the sample. So we compute the number of posterior samples that are smaller than the value we simulated. And across all of our simulations, this rank should be uniformly distributed between 0 and s, the number of samples we used. So if you think about this for a while, we have exactly that number of observation of simulations within this credible interval. So this uniformity tells us that simultaneously for all, and this then lets us explore visually what's wrong with our model. So we could have, if there's a uniform distribution of our ranks, as in the first picture, then we can be, it tells us something that the model probably somehow a bit works. Or the model can be too certain and we have overabundance of low ranks and overabundance of high ranks, which means that the true values are often outside even the 99% credible intervals. And there's something wrong with our model. Or it could be too certain and we have too many ranks in the middle. So if you ran 10 simulations and every time your simulated value was exactly in the middle of your posterior distribution, that's suspicious. It means that the intervals are probably too wide and should be narrower. Or we can see them as underestimating, overestimating, all sorts of other different cases. And so this is the core consistency requirement of SBC that we hope to use, and it lets us use computational power to verify that we don't have a big problem in our model. So that's it for the introduction to what SBC is. I hope everybody who wasn't aware of SBC, what SBC is for, now has at least a basic idea. It's a form of checking consistency of our simulated data with our model across a large number of simulations. And with that, we are gonna move to our first talk, which is from Timo, and it's about improving on those visualizations and understanding what our models do and don't do.
Hello everyone, my name is Teemu Säilynoja and I work as a doctoral candidate in Aalto University. Today I'm going to talk to you about our recent paper with Paul Bergner and Aki Vehtari titled Graphical Test for Discrete Uniformity and its applications in goodness of fit evaluation and multiple sample comparison. I'm going to focus on the test for discrete uniformity as that's the most relevant part regarding SBC. The original SBC paper also focuses on graphical inspection of the uniformity of the rank statistics and uses mostly histograms with confidence intervals for individual bins. Towards the end of the paper, Ecdf plots are added to provide another way of inspecting deviations from uniformity. But as you can see, an issue with histograms is that depending on the binning, we may arrive at different conclusions about the uniformity of our sample. Another flaw histograms with individual confidence intervals is that they do not take into account dependency between the bin heights. And in other words, if one side of the histogram bins would be lower or tend to be lower than the other side, it would be up to the viewer to notice this, and this would probably tell about under or overestimation in the model. This is where in our paper, we look at the sample Ecdf and provide methods to compute simultaneous confidence bands for the Ecdf plot. For example, here I've drawn 95% simultaneous confidence bands, meaning that in 95% of the cases, the whole Ecdf should stay within these bands if it originates from a uniform distribution. In general, we recommend using as many evaluation points for the Ecdf as there are sample values, but not going over the number of possible discrete sample values. So for example, in SBC, don't go over the number of posterior samples, as that's the maximum number of distinct rank values that you can have for the prior sample to be ranked as. That's, for example, if you have 100 posterior samples, we would only have 100 evaluation points for the Ecdf, even if we would have more than 100 repetitions of the SBC. Another important plot that we look at is the Ecdf difference plot, which is very useful, especially with large samples, as it uses the area of the plot more dynamically. Next, I will briefly introduce how to determine these simultaneous confidence bands, and then give examples of model issues that you can identify with the method. And then I will, in the end, give some practical tips and point out other uses of this method and some related future work. But so let's start with by discussing the simultaneous confidence bands. We begin by looking at the marginal distribution of the Ecdf values. With the sample from the uniform distribution and a fixed evaluation point set I, the Ecdf value is defined as the relative rank of the evaluation point set I. Here I don't mention the discreteness anymore, but by choosing the set I to lie at the possible discrete values, possibly after scaling to the interval 1 to 0, we can have the same properties as here. So for example, for a single draw to be smaller than set I, as the draws are uniform, we have the probability quite straightforwardly, and this gives us the marginal distribution for the Ecdf. Next, we move to using this marginal distribution to provide simultaneous confidence bands with equal tail probability. That is, the Ecdf is as likely to fall under the confidence bands as it is to go over them. So the first method I'm going to introduce for determining these confidence bands is the simulation method, where our goal is to define the simultaneous confidence bands for uniformity of the sample Ecdf for a given alpha that lies between 0 and 1. This method is inspired by a similar method for continuous distributions introduced by Aldo Neumann, Brown, Puja, Rolke, and Stein in 2013. First, we choose a capital M, which is the number of simulations we are going to run. So here we can affect how computationally intensive this method is. We begin by simulating just one sample from the uniform distribution, and we draw its Ecdf or compute its Ecdf values at each of our evaluation points. Then we compute the probability of each of these Ecdf values, and we compute both of the tail probabilities, so upper and lower tail probability, and we compute them so that our goal is to have bands that include the boundary into the interior, which is often done for discrete statistical tests. Then we record the smallest of these probabilities because this would already allow us to draw bands around this particular ECDF so that the ECDF is barely covered. And we repeat this step m times. And then we select gamma from among these recorded values to be the 100 times alpha percentile of the recorded values. And with this gamma, we can then compute the simultaneous confidence bands for the ECDF. So now a random ECDF from a uniform sample should stay within these boundaries with our desired confidence rate. Though this method already works well, and it has one major benefit that I'm going to return to, but for testing the uniformity of a single sample, as we are doing in SBC, there's a much faster method for determining the confidence bands that doesn't require any simulation. And that's the optimization method, where our goal is to compute this probability of the ECDF staying within the bands with a given gamma. And then we optimize gamma to get as close as possible to the desired confidence level. But the discreteness of the problem makes it so that there's not always an exact solution. And that's why we need to do optimization. The probability from the first line can be expanded. We just substitute in the upper and lower limits, and then we can scale everything by n without affecting the probability. And here in the middle, we see the scaled ECDF, which we are going to continue observing as it provides us with more straightforward notation. Speaking of notations, I'll introduce 3 shorthands for quite intuitive concepts to keep the notation in the next slide more manageable. So we are going to use R for the value of the scaled ECDF, as actually what the value is the rank of Zi among our original sample. So R is quite reasonable there. Then the next, we are going to use capital I for the interior of the confidence bands at a given location. Note again that the edges are included in the interior, or the boundaries are included. And last, we need capital T for the set of ECDF trajectories that stay within the confined confidence bands at the evaluation point. Here I also use another notation that maybe I should have said 4, but the lowercase t for a single trajectory is not really used so much. Note that we can now write the expression from within the probability from the last slide in a more compact way. So we are just looking for a trajectory that stays within the intervals, or belongs to the group of trajectories that stay within all of the intervals from 0 to k, where k is the number of evaluation points we have. So now we can finally move to solving the probability for staying within the confidence bands for a given gamma. And an important quality we are going to use is that given a sample of independent draws from the uniform distribution and the scaled ECDF value at an evaluation point, the remaining draws not yet covered by the ECDF are uniformly distributed on the remaining part of the unit interval. So from Zi to 1. And the growth from Ri to Ri plus 1, so to the next value of the scaled ECDF, is again binomially distributed, but this time we just have n minus Ri trials. And the probability for success is then scaled also regarding in respect to the remaining interval. This allows us to solve the probability of the whole ECDF staying within the confidence bands interval through recursion. So as the probability of the ECDF that has stayed within the confidence bands for the first I steps staying within the bands for the next step can be computed by computing the probability of each of the possible transitions separately. And then we just continue this to the left as the ECDF is always 0 at 0. So the recursion starts here. The probability is monotonously decreasing with respect to gamma, which gives us a convex optimization problem that can be handled, for example, with the optimized function in R. So now that we can make the confidence bands, I'll quickly tell you how to read the ECDF plots for some common discrepancies. One issue that is really easy to detect is the difference between variation in the posterior and prior distributions. For example, if the posterior is too wide, the ECDF will have a distinct S shape, as most of the probability mass is covered in the middle ranks. For the reverse case, also the ECDF plot is then reversed. Another issue that's detected with these ECDF plots quite clearly is if the model under or overestimates the parameter. So because if there's underestimations, the ECDF will fall under the expected growth, and reversely for overestimation. Note that for most of these cases that I showed you, the histogram confidence intervals were never exceeded, as that would require taking into account the dependency between the bin values. To end my presentation, I'll give you some practical tips as I promised. So even though the datasets in SBC are independent from each other, you might have autocorrelation in the posterior draws, and that might bring issues for estimating the extreme ranks. So if the sampling is really computationally intensive, you can sample without thinning, but then remember that you might have artifacts on the side near the edges of the ranks, so edges of the ECDF plots. To remove the autocorrelation, I recommend thinning the posterior samples. And again, the optimization method is the faster one for single sample uniformity test. What's what we are using in SBC. Outside of SBC, you're not limited to just checking for uniformity. You can check for goodness of fit to a given distribution if you have a way to estimate, to sample the target distribution or estimate its cumulative distribution function. Also, we can extend this to multiple sample comparison, which is a good graphical test, for example, in MC convergence diagnostics. Instead of the trace spots, we could use this to detect issues in sampling. Following work related to the article, we want to extend the method to also work with discrete distributions. So if the prior and posterior are discrete, the ranks are not necessarily uniquely defined, and depending on how you define the ranks, the distribution of the ECDF might differ. So we need to smooth these ranks. There's already a randomized method for this in the SBC package, but some further work is needed. And another useful thing related to this paper would be to provide recommendations on thinning strategies, as that's usually not quite clear what to choose, and you're balancing between having enough samples and having independent samples. But that's it for me today. Thank you for listening. If you have any questions, we have some time for Q&A next. Thank you. Yes, thank you everyone for listening to the pre-recorded talk. If you have any questions, feel free to post them onto Q&A, or, well, yeah, post them there, so then it's easy for me to see all of the questions and answer them. Make sure that I answer them all.
Okay, there is one question from Martin.
Yeah.
How to interpret the magnitude? Yeah.
Yeah, so actually, in the Ecdf difference plot, the scale of the plot is quite useful. So for example, now I need to find my last page, but in the scale of the plot actually tells you already kind of how much you are behind or ahead of the expected growth. So for example, if our difference plot would show a value of 0.1, it means that we are 10% above the expected growth at that point. So the scale on the plot is actually meaningful.
I have one question from the talk. You have mentioned that optimization method is faster for single sample uniformity tests, and I was wondering what is the opposite or non-single sample uniformity test, and do you have any other scenarios where you recommend simulation tests?
So the simulation method is useful for basically what's the opposite of single sample case is the multi-sample comparison. So if you want to know if two or more samples originate from the same distribution, and in that case, the optimization method suffers just from the magnitude of combinatorics. So there are too many combinations to just go recursively back, and the simulation method can then find the bands in a reasonable time for already quite large samples. Yeah. And Shin seems to be asking, how does autocorrelation affect the extreme lengths? So usually if we are sampling the posterior with an autocorrelated chain, the samples tend to not explore the tails of the distribution very well, which results in that in the SBC showing these really large spikes in the edges of the rank histograms. So for the Ecdf plots, that would mean that the Ecdf grows really sharply in the beginning, and then even if otherwise the sampling would be good, it tapers down a bit to compensate the original growth, and then in the end, so in the very last high ranks, it again has a sharp spike. So it's compared to the case where your posterior would be just too narrow, so your model would be too certain. There, the tails of the distribution tend to be a bit more, like the growth in the tails is more kind of, it's not as sharp. Yeah. And the autocorrelation actually shows like quite high sharp spikes in the ends.
We have another question from Denmark.
So disadvantages of the Ecdf plots related to the histograms. Well, one case that is not as common, but if your model would be kind of, if there would be a certain bin in the histograms that always is really high, but it's kind of in the middle of the distribution, your ECDF might not grow out of the bounds just based on that one bin. So if there would be a certain rank for some case that you would be just getting the certain rank more often, maybe in the bins, in the histograms, that would be more visible, but then you would need to be repeating your SBC to see that this behavior actually repeats quite often, or run a lot of SBC tests. At least that's something that comes to my mind, because the ECDF plots is strong when you want to see the dependency between the different ranks.
I also had similar experience. Like, do we have to care for the parameter k when we are doing ECDF diff plots?
Well, yeah. So the k was the number of evaluation points. If in SBC you compute ranks, so you have a discrete distribution of possible values. So you have a discrete uniform distribution of ranks, or you hope to have uniform, but at least it's a discrete distribution anyway. So then I would pick k to be equal to the number of possible ranks. So after thinning the posterior distribution, if you're thinning it, which if your sampling is not really intensive or hard, like computationally intensive, you should thin to get the autocorrelation out. If there's autocorrelation, usually there's at least some. And yeah, lost my thought. Yes, so having the k to be the maximum number of distinct ranks. If you have it lower, then you have a lower resolution ECDF. Anyway, the bands are then your requested confidence bands. So, but it might, you don't see everything so nicely in the ECDF. So kind of you can use the maximum resolution that you have available based on your posterior sampling. If you have a very small sample size, so you only run maybe 10 SBC repetitions, but you have each of those has a posterior sample the size of 1,000 samples. Then if you have 1,000 estimation points, your ECDF will look funny to the eye. It is a valid, and it's a kind of, you are trying to evaluate it at so many points that especially if you're plotting 95% central intervals, the ECDF is expected to get to the maximum 10 already quite much before the end of the possible ranks, and then the difference plot will show like a descending step function there in the end, which might look funny. So if you have a very small sample, you should anyway, you can use the number of posterior draws, but don't use the ECDF difference plot, then use just the normal ECDF plot.
Okay.
Because for small samples, that's already quite clear. The range is, and the confidence bands are so wide that from that you can actually see much better. Or yeah, you see better, and you don't see the funny step function going down, which might confuse.
That's very interesting. Yeah. Thanks for the first talk, Timo. Yeah.
Thank you.
Let's move on to Paul's next talk.
Hello and welcome everybody. This is my talk on price specification in the context of simulation-based calibration, and my name is Paul Bergner from the Cluster of Excellence Simta, University of Stuttgart in Germany. To give you a little bit of context, so in simulation-based calibration, SBC, which you are knowing by now, as you know, we repeatedly sample parameter values from the prior. And that immediately has some implications on the relation of SBC and priors, which is there is no simulation-based calibration without a prior. We always need a prior, no matter if in the end we're going to use some weakly informative, perhaps like really wide priors. For SBC, the prior will matter in any case. And we can see that, and I'm going to also demonstrate that is that for the same model, for the same likelihood, different priors may imply different SBC results. That is, for some priors, we may see well-calibrated behavior in some parameters, and for other priors, we may not see this, right? So prior specification is an important part in SBC, and there is no SBC without prior specification. So we need to think about prior specification whenever we do SBC. However, in contrast, in practice, many prior choices are somewhat ad hoc and perhaps not really nicely working together with SBC. For example, often we're using independent weakly informative priors. With independent, I mean that each parameter receives its own prior that is independent from the prior of all or most other parameters. And with weakly informative, I mean that we have quite wide priors that rule out like extremely implausible, really extreme values, but leaving the rest of the parameter space relatively untouched. In a lot of cases, we simply use the default price of the software unaltered. That is, whatever the software gives us as price, at least I often tend to use in my analysis, hoping that the data has enough information that this choice doesn't matter. But keep in mind that for SBC, the prior specification always matters. So perhaps the common practical choices we are making, often enough, of weakly informative and independent priors are not ideal for SBC. So what does that imply for SBC in practice? Let's consider for a start Bayesian linear regression with some independent priors on our regression coefficients. So in Bayesian Gaussian linear regression, the likelihood is normal, so y is our response variable. It's normally distributed around some mean mu and some standard deviation sigma, where mu is predicted by some covariates and sigma is assumed constant across observations. And in linear regression, mu would be an intercept b0 plus the sum of some regression coefficients bk, each multiplied by the specific predictor or covariate xk. So as parameters, we have our intercept b0, our other regression coefficients bk, and our residual standard deviation sigma. And for example, some more or less ad hoc, independent and depending on the scale of the variables, weakly informative priors we could choose, for example, on b0, a normal prior with mean 0 and standard deviation 5, a normal prior with mean 0 standard deviation 1 for the other regression coefficients, and exponential prior with rate 1 for sigma. And before we're going to dive into SBC, I want to show how such independent, supposedly weakly informative priors may actually be quite informative depending on the metric we are looking at. So suppose we are looking at the percentage of explained variance or coefficient of determination r squared, which we can, for example, define as 1 minus the residual variance sigma squared divided by the total variance of y, or equivalently as the variance of mu divided by the variance of mu plus sigma squared. So what does our independent weakly informative priors that are looking okay for our individual regression coefficients imply for the percentage of explained variance, a priori without seeing any data? And this is what we see. So as we increase the number of predictors from 1 to 15, our implied prior on the r squared changes from almost uniform for 1 and 2 predictors to extremely spiked at 1, that is 100% a priori explained variance as expected by the model and the prior, if we increase the number of predictors to 15, and of course the spike gets more extreme for increasing number of predictors. That is, for increasing number of parameters in our model, each of which receives independent priors, our priors will overfit. In this case, overfit is here indicated by an r squared of close to 1. And I'm saying overfit because in practice, we almost never have 100% explained variance. We perhaps have a few percent, perhaps we have 10 or 20 or even 30% or something, but we will never have like, or almost never have 99 or even close to 100% explained variance. So independent priors in enough abundance will overfit and have like too much signal in a way that is expected in actual real data. So they are not good priors. The question is, does that affect SBC? And in linear regression, it doesn't really, as we can see, right? So this is our Ecdf difference plots for linear regression for the B coefficients. So the light blue area is the place where we expect the Ecdf difference plots to be if things are well calibrated. And in this case here for the B coefficients B1 and B2, everything looks good. Same for our intercept B0 and same for the residual standard deviation sigma. So our prior overfit drastically, but when running SBC with Stan in this case, it doesn't really matter. And the reason is that the normal distribution is like super numerically stable. We don't have any nonlinear transformation. Everything is linear. So even if we overfit drastically, SBC will just do well, like Stan will do well, and SBC indicates that Stan is doing well in this case. But what happens if we move from linear regression to generalized linear regression? For example, instead of using a normal likelihood, let's use a gamma likelihood with mean 0 and an additional parameter alpha, which is kind of the shape of this gamma distribution. So the gamma distribution is used for positive data, and to make sure that our predictor is positive, we're going to use a log link or equivalently an exponential response functions. So we're changing two things. We're changing the normal likelihood to a gamma likelihood, and we are using a log link or exponential response function, so that mu is now exp of our linear predictor term. And the gamma distribution generally is less numerically stable than the normal distribution, and also our exponential transform kind of leads to some explosions of very high linear predictor terms, which may happen if we use weakly informative priors. So let's use some weakly informative priors. For example, on B0, normal distribution with mean 2 and standard deviation 5. It doesn't really matter if we choose mean 2 or mean 0 or mean 1. I just choose 2 for convenience, so that in expectation our a priori values are not too close to 0. We use the same normal 0, 1 prior on the regression coefficients, and we use a gamma prior with shape 0.01 and rate 0.01 for alpha, which happens to be the default prior of the shape in BRMS. I don't know how I came up with it. It's probably not a good choice, as we're going to see in a second. So let's check what this data generation implies for, or that this model implies for a priori data generation. So data generated with gamma regression in terms of prior predictive checks. And we see stuff is wild, right? And this is a well-behaved data set. I didn't show you really badly behaved data sets. So most of those predictions are 0. You can't see that from the plot, but they are literally almost 0. So 1 to the power of minus 10, 1 times 10 to the power of minus 30 or something. So very close to 0, and some really big outliers above 200,000, for example. So this isn't great, and this is a well-behaved data set. So it's not surprising if SBC with Stan would fail just for numerical reason, because a lot of stuff is close to 0 and some are very far away from 0. So this is not realistic data. And we see indeed with these priors things break down. So this is SBC Ecdf difference plots for the regression coefficients B1 and B2. It completely fails, and if we do the same for the intercept and the shape, both of which completely fails. So let's try to fix that a bit. So suppose for the intercept, instead of choosing a normal 2-5 prior, we're going to choose a normal 2-2 prior. So reducing the standard deviation of the intercept, changing one of the independent priors and seeing how it goes. And indeed now the Ecdf difference plots for B1 and B2 actually look quite good, but unfortunately for the intercept and the shape, things still fail. We could work like by changing additional priors, for example, on the shape parameter to also fix that. I'm not going to do this now. The point is, if we have enough weakly informative independent priors on our parameters and some nonlinear transforms or not numerically stable likelihoods, things may become quite weird for SBC because the data is just overly complex. We're generating weird data a priori, which is not realistic at all and creates trouble for SBC. So what are we going to do about that? So how do we avoid prior overfitting, and at the same time, by doing this, also ensure that SBC has a higher chance of actually doing well and not run into any kind of numerical problems? And I don't present evidence, but the general direction I think we should be going are hierarchical joint priors. So Usually, when we have a vector of parameters theta from theta1 to theta k, and we would be setting independent priors on each of them. Think of the thetas as regression coefficients. In our examples, we specified independent priors of each of them. Now, this is not what we're going to do in hierarchical joint priors. What we're going to do is we're specifying a prior, or like priors, each of which depends on the same set of hyperparameters lambda. And those hyperparameters are not fixed and chosen by the user, but they are itself parameters as estimated by the model, so we have a hierarchical prior structure. So for each theta k, the prior on theta k depends on the hyperparameter vector lambda. And this lambda in turn has a prior where each of the lambdas has some prior that then depends on some vector of values tau that are low dimensional and user choosable. That is, instead of specifying a prior on our main parameters theta directly, we're going to let theta depend on some hyperparameters lambda and choose lambda like in a clever manner so that it is highly structured, or in a way that L is much smaller than K, so that we have much fewer hyperparameters than we have kind of original main parameters, for example, regression coefficients. And then we only let the user choose the priors on our hyperparameters lambda. And if we set up this hierarchical structure correctly, then we can achieve a prior that controls the overall complexity instead of controlling the complexity of each term, controlling the overall complexity. Examples for that are the R2D2 prior, I'm showing the DOI here, or the regularized horseshoe prior. So for example, in the R2D2 prior, one of our hyperparameters would actually be the percentage of explained variance would actually be R squared. That is, we would turn around the logic we have used at the start. So instead of specifying independent priors and the regression coefficients, and then looking at those implications for the R squared, we're specifying a prior directly on the R squared. That is, we're controlling R squared, we're controlling the overfitting, and then we propagate this hyperparameter, the uncertainty in the hyperparameters, down to the original regression coefficients. But by specifying the priors like this, we're making sure that the R squared distribution is as we said it, and then the prior on the regression coefficients just follow. That is, we turn around the logic of prior specification from independent to implications for R squared So we're turning around the specification of priors from independent priors and then looking at those implications for the hyperparameters or hyper measures of model fit such as R squared, to a way where we're specifying those fit measures, those hyperparameters and priors on them, for example, R squared, and looking what that implies for the vector of original parameters for the vector of regression coefficients, for example. To wrap up, given enough parameters, independent priors will overfit, and this can compromise SBC in models with nonlinear transformations, as we have seen in our gamma regression setting. My hypothesis is that joint priors provide a path towards not only solving the problem with overfitting, but also solving the problem with SBC running into problems for those overfitting priors in nonlinear transformed models, because we're controlling the overall complexity, and that avoids numerical problems in our likelihood or in our model more generally, and thus yields better chances of SBC working well. Thank you so much for attending my talk, and I am looking forward to answering your questions.
Thanks for your talk, Paul. We have first questions from Jordan Jongerling. Yeah.
Okay, so for everybody, I'm going to read the question again. Hi, by the way. If I have a set of priors based on substantive knowledge or prior research, but those aren't well suited for SBC, tweak the priors anyway for the sake of SBC, not use SBC something else? Yeah, that's a really good question. And I don't have a good answer. So I'm trying to approach it in some way, hoping that it's helpful. So if you have some set of independent priors, you mean independent priors based on your substantive knowledge, and those aren't well suited for SBC, as it may turn out, suppose you've been running this, right? Or if you're using SBC and it kind of fails. That means your priors do not convey enough substantive knowledge to generate realistic data. Suppose that your algorithm, for example, the Stan estimation algorithm works well. And the general problem actually comes down to this prior overfitting. That is, you may have substantive knowledge on your individual priors, that is on the marginal priors for each parameters, but you may not have that substantive knowledge on the relation of these parameters, on the dependency, which is in fact what the joint priors would imply. And so it's good to use that knowledge, but perhaps if you're running these and you're using SBC and it fails, even though you perhaps trust the Stan algorithm with these, then you should be adding some knowledge or some information on likely relation between the parameters, which I know is difficult, and I don't have a good recommendation of how to come up with this. Another way to put it, if you had a joint prior and you would have substantive knowledge on the hyperparameters of that joint prior, for example, on an R squared and an R square like prior, then you could use that substantive knowledge and let the rest of the prevention of overfitting being figured out by the prior itself. Suppose none of these options are possible, which is a likely outcome in a lot of cases, then I'm not sure if SBC is the best way to approach things in a way, because you have your prior, but it's too wide for the actual data. And so perhaps SBC doesn't give you reliable results, or like indicates that like SBC fails, even though for real data or data that would be similar to the real data, it would actually work. But this is something we don't know. So in this case, you can run SBC, but your results may not tell you something about how well things will work for realistic data, but then simply the fact that your model, including the prior, is not a realistic a priori description of your data, which may or may not be a problem depending on how much data you're actually having and how informative the data are. I know it's not a really precise answer, but what I can tell you, this is something we are working on prior specification, making prior specification easier, like coming up with principles of prior specification, and of course also how to include substantive knowledge and prior research into priors in a way that we actually come up with realistic priors.
We are slightly running late, so like we'll have one more questions. Is R2D2 prior the same as the R10 ARM prior?
No, the R2D2 prior is by Sang et al. You can, I posted the DOI in the slides, you can look it up. But they're both inspired by the same idea of specifying a prior on R squared and then like seeing what that implies in terms of the regression coefficients.
Okay. Let's make the last question quick. About the joint prior.
But the joint prior, a multivariate normal would do the trick, or is it more like coefficient regularization? A multivariate normal would do the trick if you specify the covariance / correlation matrix in a way that it would actually prevent overfitting. So suppose all your regression coefficients would be independent, all your predictors would be independent, but you would specify like highly correlated multivariate normal distribution, highly positively correlated, then you would even increase overfitting. So you would need some kind of negative correlation, or you would need some kind of correlation in the prior that kind of goes in the other direction than your correlation of your predictors to take these kind of things into account. So yes, a multivariate normal would do the trick if you set up your correlation matrix correctly according to the correlation structure of your predictor terms, and that's not necessarily a trivial thing. I'm giving you one name of a prior that actually does something in that direction, which is Selness G prior, if you want to look it up. This is also some research we're doing in this regard that may be helpful in this direction.
Thank you very much.
Thank you for attending my talk.
Yep.
Hello, everyone. Thank you very much for inviting me. I'm excited to talk here. I will present my work on workflow techniques for the robust use of base vectors. And this is work in common with Bruno Niesenbaum, Paul Birkner, Michael Bettencourt, and Shravan Vasisht, and is based on an archive paper on this topic. A brief overview of the content. I will briefly introduce base vectors, and then I will talk about estimation or error of base vectors, including the stability or variance, accuracy and bias, and about data variability. Then I will present results from some simulation studies that we conducted, and will conclude with the base vector workflow. First, on base vectors, when we compute the posterior probability of some model given some data, this can be computed by taking the prior probability for the model and multiplying that with the model likelihood. So the likelihood of the data given the model. And this likelihood term is also often termed the marginal likelihood, because so this is computed by taking the likelihood of the data of the parameters of the data given the parameters on the model, multiplied by the prior of the prior probability of the parameters, and then we can integrate out the parameters and obtain this marginal likelihood term. So what happens if we have multiple models? If we have two models, we can take a ratio of model posteriors, so we can have the posterior probability for one model divided by the posterior probability for another model. That's the posterior ratio, and this can be computed based on the prior odds. So the prior probability for model 1 divided by the probability for model 2. And then we have this term that is called the base vector, which is the marginal likelihood for model 1 divided by model 2. So this can be written like that. Base vector for model 1 over 2 is just the ratio of these marginal likelihoods, and the base vector provides relative evidence that the data provide for model 1 over model 2. So this is how where the data enters the equation to compute the relative evidence. If the base vector has a value larger than 1, then this provides evidence for model 1. And if the base vector has a value smaller than 1, this provides relative evidence for the model 2. Note that the marginal likelihood here plays the key role for providing relative evidence for each of the models. Thus, it's important to take a look at how this marginal likelihood is computed. And I just want to note that the prior for the model parameters plays a key role in this computation. So the model is evaluated under the prior assumptions, on the prior parameter values. So in this setting, the priors and the model parameters have an even stronger influence on base vectors as compared to their influence on posterior estimation on parameter values. And last, we want to have a posterior model probabilities when we have multiple models. And to compute that posterior probability, we can just take the posterior for one model and divide it by the sum across all models. Okay, so how would our theoretical workflow with the base vector look like in the setting? So this is illustrated using the dark red arrows here. So we want to take our data and our model. From that, we want to derive our base vector and use that to perform inferences and possibly decisions. However, for most interesting problems, there are no analytical base vectors available. Instead, we have to rely on approximations. In the work I present here, we rely on bridge sampling based on posterior MC draws. So what this gives us is a base vector estimate, an estimator of the base vector. So this is what, in practice, our workflow looks like. And this estimator will be used to perform inferences and possibly decisions. So in this situation, we really want to know the quality of the estimator that we have. So we have to investigate this quality, and that's what we do here. So what are different kinds of errors that we can observe in base vector estimation? First, we have to estimate the stability of the estimator with MC draws. So this corresponds to the variance of the estimator. How can we investigate that? We can use fixed data, perform repeated MC draws using bridge sampling to repeatedly estimate the base factor, and then we can look how variable these base factor estimates are. A second question we can ask is how close is the base factor estimate to the true base factor? So the question is there bias in our estimation procedure? So systematic bias that the estimate deviates from the truth. And for realistic complex models, there are no guarantees that the base factor estimates are correct. Given that the inferences that we perform with the data, vary with the data, what we need to do in each situation is we need to calibrate our base factors. We can do that using prior predictive simulations or simulation in the procedure known as simulation-based calibration. A third question that we ask is how variable are base factors with the data? So only because we can obtain some base factor from the data doesn't mean that this is provides a lot of information, because if the data are sampled with considerable noise, this base factor can be very variable from one data set to the next. So we can investigate that using the same simulations as from the SBC, but we also here show an analysis with posterior predictive simulations. To investigate these issues, we perform some simulation studies based on an artificial experiment where we have a within subject manipulation factor X, with sum coding -1 + 1, 15 subjects, 2 data points per subject and condition, and we assume log normally distributed response times as our dependent variable. We assume a nested model comparison situation where we have an alternative hypothesis H1, which assumes that there's an experimental effect in the data. So our log response times are modeled based on an intercept and a fixed effect, which is a factor X, and on random intercepts, random slopes, and random correlations varying across subjects. And then we have a null hypothesis, H0, where we assume there's no effect of X. So no difference between experimental conditions. So it's the exact same hierarchical model as used in the alternative hypothesis, just that the fixed effect for factor X is missing. So we assume that on average, the response times are the same in the two experimental conditions. And we assume priors for the models, 50% each, say they equally likely, and we assume priors for the parameters, we will define them. And for analysis, we use R packages, BRMS for posterior inference, and bridge sampling to obtain base vectors. So first, we investigate the stability of the base vector against MC draws. For that, as I said before, we use fixed data. We perform 100 base vector estimates for the same data set using repeated MC sampling. And the sampling by default is based on 2,000 samples, and we also test how this changes when we use 10,000 samples for the estimator. And these are the results. On the left here, in the middle here, we see histograms of base factor estimates. And note that the x-axis is on the log 10 base factor scale. And with 2,000 MC samples, we see a large variance of the resulting base vector, each on the same data set, but very different base vector results. And this variance is much reduced when we use 10,000 samples, but there's still variance. So when we look on the right-hand side here, this shows the log 10 standard deviation of base vector estimates. We see they're very variable when we have limited number of samples, and this variance gets much reduced when we have more samples. So this simply shows that simply having an estimate for the base vector doesn't need to tell you anything about your data. Maybe this is just completely variable because you didn't use enough MC samples in your bridge sampling approach. So it's really important to check for your data whether you have a stable estimate or whether you need to increase your your sample size to get more stable estimates. The second issue we investigate is simulation-based calibration to test the accuracy of base vectors. So simulation-based calibration tests the accuracy of bias. So mathematically, we can say that we have here where we take the prior probability for a model, sample a model from that, then we can take that model to simulate artificial data by using the prior parameter distributions to simulate parameters. And there's a hidden integral here. And then based on the simulated data, we can perform posterior inferences. We can compute the posterior probability of a given model given the simulated data. And if we average this across data sets and models, we get an average posterior probability. And this average posterior probability, if the inference procedure works correctly, this should be the same as the prior probability. So that means if our estimate, our base factor estimate, is accurate and not biased, then the average posterior model probability should be the same as the prior model probability. And we investigated this here. So as I said before, model priors were set to 50% each. We had the parameter priors. And then we performed 500 runs of simulation-based calibration. First, we draw, just to repeat the same process in a less mathematical way. First, draw the model from the prior. So with 50% probability, we draw the H1 and otherwise the H0. Then we draw model parameters from their priors and we sample them. And then we can use these to simulate artificial data. And based on this simulated data, we can estimate the models again and estimate base factors. Then we have a base factor estimate based on the simulated data, and we can use that to compute posterior model probabilities. And now the average posterior model probability should be exactly 50%, for the alternative hypothesis should be exactly 50%, because that was our prior. And we did this here, we ran these analysis, and we found that in this situation, the average posterior was actually pretty close to 50%, with a frequentist confidence interval ranging from 45 to 54. So this suggests that really in this situation, we don't have any evidence that there is bias in the base factor estimation. So the base factor seems to be computed accurately. Importantly, you really have to check this for each individual the experimental design and data analysis situation, ideally at least, because this is just initial evidence that this might be accurate, but in other situations this could differ. So this has to be checked. So what we tried, we played around a bit here. We varied the prior probability for the H0 between a value of 0 and 1. So if the computation is accurate, the posterior probability plotted on the y-axis should be the same as the prior. So it should be right on the diagonal. And we see that the data actually fall directly on the diagonal. So there's evidence that this estimation is accurate. Okay, so we had seen before that with 2,000 samples, MC samples, the estimate gets very variable. So what happens with the accuracy of the estimate in this situation? And we see that the average posterior probability for the H1 is still very close to 50%, confidence interval ranging between 44 and 53. So a small number of MC samples seems to result in a high variance of the estimator, but not in a bias. So next we look at model misspecification, how that impacts on SBC simulation-based calibration. So in frequent generalized linear mixed effect models, it is known that leaving out random slopes from an estimate from a model can lead to alpha error inflation, so false support for the alternative hypothesis. So we did this here by comparing two models. The first has a fixed effect for the factor, x. The second one is lacking this fixed effect, again, an alternative and a null model. But importantly, now the random slopes are missing. So we're assuming that the difference between conditions is the same for each individual subject. And if we do simulation-based calibration on these models, we see that now the average posterior model probability for the H1 is not 50 anymore. It's 58, with the confidence intervals ranging between 54 and 62. So this indicates that there's clear bias in the base factor estimate. the posterior probabilities provide too much support for the alternative hypothesis. So this is just an example. This could happen in other situations and should be checked. As the third approach to look at errors in the estimation of base vectors, we look at data variability. So we can use the same set of prior predictive simulations that we used in the simulation-based calibration, but we can now look across 500 simulated data sets. How variable is the base vector across data sets? And we see that if the true hypothesis that was sampled is the alternative hypothesis here on the right side, then we find base vectors that provide a very strong evidence for the alternative, but also strong evidence for the null. So so a single base vector could, although the alternative hypothesis is true, could result in any kind of outcome. And a similar thing is true for if the null hypothesis was simulated, it was the true in the simulations. So a base vector from an individual data set does not have to be very informative about our hypothesis in question. And we should have a look at these, at how variable base vectors are for our data set. So to check this for a more realistic data analysis situation, we looked at agreement attraction, a psycholinguistic phenomenon that is thought to be very robust. And we performed posterior predictive simulations based on empirical data. So we used a study with 32 subjects and looked at the base vector based on posterior predictive data. And we found that the base vector plotted on the y-axis here varied across simulated data sets between strong support for the alternative, but also to moderate support for the null hypothesis. So very different results depending on the data set that you by chance obtained. However, when we use a data set with 180 subjects and again perform posterior predictive simulations, then the base vector estimate across 50 simulated subjects is very stable. So there's always nearly the same base vector estimate. So we can really rely on an individual data set, a base vector, if we have such a large sample size. By the way, the x-axis here shows the effect size, so the difference estimated difference between experimental conditions. Okay, let's conclude with the base vector workflow that we suggest to perform when working with base vectors. First, we should define an observational model and priors for the model and for the parameters. And then we should check the stability of the base vector with MC-MC cross, so the variance of the estimator, by estimating the base vector on the same data set multiple times to know whether we get a stable estimate. And second, we should ideally perform simulation-based calibration to test whether the base vector estimate is accurate or whether it has bias for our specific data analysis situation. Third, we should investigate the data. We can use that same set of simulations to investigate the data variability of our inferences and to see whether our base vector is highly variable or quite stable based on the data that we have. And if the results are accurate and if the base vector estimates are accurate and reliable based on this analysis, we can compute the base vector for our empirical data and use it for inference. Otherwise, we should improve the experimental design or acknowledge limitations. Last, I want to briefly say that so far we're talking about inferences, which is a continuous thing, but you can also be tempted to perform decisions like claiming discovery. However, decision-making is often premature because, as I said before, there's data variability, and often decisions are based on heuristics, such as a base vector larger than 10 is used to claim discovery. However, if principled decisions are needed, then you have to actually define something called utility functions. And this is the second part of the base vector workflow that we write about in the archive paper that I don't have time to go into detail here. With that, I want to thank you very much for your attention. I want to thank my co-authors again for their great contribution and help, and I'm happy to take any questions. Thank you.
Okay, thanks for your talk. And we have a question from Louis. It says, do you expect problems when the prior model probabilities are far away from 50%, or when you have many models with a multi-model distribution?
Okay, hi everyone. Yeah, that's. I'm not sure I have a good answer to that question, actually. I'm not sure what kind of problems you're expecting. Of course, if the prior model probabilities are far away from 50%, that is one of the simulations that I showed, where where all the data points were lying on the diagonal. So actually, what it turns out is that whatever prior probability you have for the model, the posterior probability should be exactly the same in the simulations. And the simulations I can, maybe I can, oh, no, I cannot share my slides. So that was this one slide where all the data was on the diagonal. And it actually, so mathematically, there should not be any problems in the simulation-based calibration. It should work out, and our simulations actually showed that this worked out as well. So we varied the prior probability for the model from 0 to 1, and the average posterior probability for the model was also just in the same way varied between 0 and 1. So it was exactly the same. There was no problem. And with the multi-model distribution, I'm not sure.
Well, so if you have a bunch of models, like 10 models, and instead of having something that's a bit uniform, you have 2 models that are very probable and the rest of the models are not, would you expect any problems with this kind of calibration?
That's an interesting question. I haven't thought about that. Sorry. I would have to speculate from the top of my head. I don't know.
Right. Thanks.
See, if we don't have any questions, I actually have a personal question. So you said like we use simulation-based calibration to figure out like how accurate the estimate is, the base factor estimation. But in which context is how is the prior predictive check used to achieve that goal?
So how is the prior predictive check used to achieve the SBC for base factors? Is that the question?
To verify the base factors were correct.
Yeah. So the prior predictive checks are of course important because, I mean, as I said in the introduction, the priors will play a huge role in base factor computations, right? So I think it's crucial to do thorough prior predictive checks to investigate whether the priors that you're assuming really make a lot of sense in the context that you want to investigate this. And one possibility, of course, is that you decide for one specific set of priors, and that's what you probably want to do if you do a simulation-based calibration. Of course, when you do base factors, another thing you might consider is sensitivity analyses, and want to try out different prior assumptions. And then, of course, if you want to combine that with simulation-based calibration, that takes. I mean, one issue with SBC is that it takes a lot of time. So if you now want to try different priors because you're not sure that your priors are correct or are good, then this takes a lot of time. But this could be one way to go. But yeah. So definitely, that's a very good point, an important point that this selecting the priors in this analysis is very important.
Thanks for the question. Speaking of time, we have a question from Eric Brown. He says, out of curiosity, how long do these simulations take? For example, how long would 500 SBC runs with 10,000 random samples take?
Yeah, thanks for the question. That's a very important question because it really takes a long time. So I have to admit that for the simulation that I showed you, I chose a very small data set and a quite simple hierarchical linear model. So with this setup, I could run these analyses in the order of days. But if you have like hours to days, but of course, if you have large data sets and complex models, this can very quickly explode. So this is clearly one of the problems with this approach. Of course, that if you want to go to realistic data and realistic models, it can take a lot of time. So we think it's still so the problem is that we don't know whether these estimators of base factors are really accurate. I mean, we have these methods, and our results suggest, if like for our simple examples, these things worked well, but for real models, we don't really know. So I mean, one solution that we suggest you could that one could do is to run such an analysis once for a given research program, where you have similar analysis, similar models, similar data sets, and just check it once. But not run it for every single analysis, because it might just be too much. But yeah, in the end, one argument you could make is better have few simulations than no simulations. But yeah, it's clearly an issue with this analysis that it's very expensive in terms of computation. Thank you.
Okay. If there's any more questions, we'll be moving on to the next talk. Once again,
okay.
Thanks.
Hi, everyone. My name is Luis. I'm a lecturer at the School of Applied Mathematics at the Getúlio Vargas Foundation in Brazil. And this is joint work with Renko Buka, who is a researcher at the University of Auckland. And today, I'm going to be talking about SBC, simulation-based calibration for phylogenetics. And what I hope to convey is what I call phylogenetic exceptionalism, meaning I'm going to try and show you that phylogenetics is a very special problem that requires that we think about certain things in a different way. All right, so phylogenetics depends fundamentally, of course, on trees, phylogenetic trees, and these trees are hypotheses about the world. They are graphs that describe hypotheses about evolutionary history, right? So hopefully you know by now that the correct hypothesis about the evolutionary history of humans, chimps, and gorillas is this middle tree here, right? So we might be inclined to think that whatever chimps and gorillas are more closely related because they are furry and, you know, or whatever, but no, actually humans and chimps diverged around about 5 million years ago, and the gorillas and the ancestor of chimps and humans diverged around about 8 million years ago. So hopefully you have noticed by now that I'm using this tree to tell a story, right? So I'm telling a story about how evolution went, right? Good. So these trees are hypotheses about the data, and of course, then we can use data to test these hypotheses and understand which of these are credible and which aren't, right? So in the case of this particular problem, we know with, you know, beyond the shadow of a doubt that this is the correct evolutionary history because we have a lot of evidence. The other thing that we can do with trees, which is slightly different from what I've shown, is we can, so if you imagine there's a an arrow of time here going downwards, this is a population that's not growing or decreasing, it's stable through time, and this is an exponentially growing population. And what I'm showing here is a process whereby we sample these red individuals, right, through time. And what we're doing here is we are tracking the ancestry between all of the red individuals. So the yellow dots here depict ancestors, unsampled ancestors, and the red dots show sampled individuals. And what's important to notice from both these trees is that the temporal sampling process imposes constraints on the tree, right? So the ancestor of these three individuals here cannot possibly live here, right? Because, you know, there's a temporal precedence constraint on this tree, and that will complicate things when we try to estimate phylogenetic trees from data coming from these red individuals, right? So there will be some structure that imposes additional constraints on tree space. And as you can see, different population dynamics will lead to different tree shapes. Hopefully that will be clearer in the next slide. So why do we care about trees? Well, there are two answers, right? The first is that we care about the actual tree because it tells a story about evolution, and we might be interested in that particular story, right? But even if you're not interested in the tree, you might be interested in making inferences conditional on the tree, right? So for instance, you can infer things about population dynamics from tree shape, and you can also infer things about migration and other processes from the clustering pattern of certain traits on the tree, right? So that means you really want to properly account for the uncertainty on the trees so you can make principled inferences about the other parameters or the other processes that you do care about. Right, so one major difference between phylogenetics as a statistical problem and most other statistical problems out there is that we can usually always find some mapping from the space of parameters, the parameter space, to a manifold, right? To RD for D, suitable D. But for trees, this is not true. It's not true at all. We can actually prove that there's no embedding of tree space onto RD for any D. So we need to be a bit clever about how we represent tree space, and some representations will be better than others. So what I'm showing here is a sort of metagraph representation of tree space, in which each vertex is a tree, and we connect these trees if they are a certain distance from one another. In particular, in this case, we're defining what we call the SPR distance. So SPR stands for subtree, prune, and regraft. So an SPR operation is I take a subtree, let's say 1 and 3 here, right? This is a subtree. I take it, I prune it, so I cut it off, and then I glue it somewhere else in a tree, turning the original tree into another one, right? And if I can turn A into B with just the one SPR operation, then they are connected in the SPR graph. And of course, if I can't, then they aren't, right? So we know a bunch of things about this graph, and it makes it easier to think about stochastic processes in the space of trees. This is just an illustration of how the sort of hoops we need to jump through to try and represent tree space in a meaningful way. Right. The next thing I would like to mention is what the target posterior distribution looks like for a phylogenetic problem, right? So little t here stands for the branching order, which in phylogenetics we confusingly call topology. Mathematicians in the audience will know that topology means something slightly different, but we usually say this is the tree topology. B here is a vector of fixed size that depends on the number of leaves, and that's the branch lengths. So we have a tree, the branching order, and also what the lengths of the individual branches are. And omega here are the parameters, other parameters that we care about, like mutation rate and migration rate and population size, all of those parameters that we might be interested in scientifically that depend on the tree somehow, right? Depend on the tree structure. And I'm well aware that we usually don't have to write the normalizing constant for our target, but the reason I wrote it down here is that we can sort of understand the difficulty, the complexity of the problem. So to obtain this normalizing constant, you would have to marginalize over the branch lengths, and that's linear in the number of leaves. Then you would have to integrate over omega, so all of those parameters, which can be really high dimensional. And then once you've done that, all you need to do is repeat that integration process for every tree in tree space. So to give you an idea of how big that space is, if you had 53, around about 53 leaves in your tree, which is not a big data set at all these days, you would have more possible trees than there are atoms in the observable universe. So something bigger than 10 to the 80. So this is an absolutely ginormous space full of terraces and, you know, flat regions. It's really hard to explore. Right. So how do we do SBC for trees then? Well, one thing we can do, and this is a solution that Remco and I came up with, is we are going to map trees to something that's on, say, the real line, and then we're going to compute ranks on that space. So to do that, what we do is we pick an anchor or focal tree, tau naught, and in this particular case, we're picking it from the prior, and then we proceed sort of normally as you would in SBC. So we draw trees from the prior, and then we compute the true distance from that tree to the anchor tree. Then we generate some data from the conditional distribution of the data and the tree. And then with that simulated data, we compute, approximately compute the posterior, and we look at the distances of each posterior sample to tau naught, our anchor tree. And then finally, we look at the ranks, right? So what we're doing here is we're projecting things in tree space to quote unquote distance space. And then in that space, because that space has well ordering, we can compute ranks, right? So that's what we do there. Right. So here I'm showing you some very preliminary results, and the results are really not important here. What's important is the discussion that will hopefully ensue from this. So I'm looking at Robson-Fultz distance. So here on the panels, we have two different methods, two different samplers. So this is state of the art. This is something that I've developed during my PhD. And here we're looking at Robson-Fultz distance, which only takes differences between branching orders into account. So it ignores branch lengths. And we're also looking at the same set of experiments, right? But using BHV distances. So BHV stands for Billera, Voigtman, and Holmes. That's a slightly complicated distance that does take branching order and branch lengths into account. So it takes the whole tree into account to compute distances. And what we see here, which is slightly worrying, and that's something that I want to share with you, is that if you look at this particular distance, you don't see any problems for either sampler. But if you look at this distance, BHV distance, then you do detect some weirdness that you would obviously want to investigate further, right? So I guess the conclusion from this set of experiments is that if you want to do SBC for trees, one thing you can do is map to a distance space. But then if you do that, nothing guarantees, that distances, that every distance will give you the same set of diagnostics. So, you know, certain distances will will highlight problems, whereas others won't. And that's slightly worrying. We can also do this for continuous parameters. So the omega there that I talked about. So this is population size. This is some phylogenetic some mutation stuff, the frequency of each nucleotide or whatever. This comes from Remco's application. So this is something that we are kind of developing and sort of mirroring the stuff that's being developed in the SBC package. So you can look at these two things. You can look at the histograms, let's say, for the tree distances, and you can also look at that for omega as you would for any other model, right? So I would like to spend a couple minutes on this last slide because I think that's quite informative to people that are not familiar with phylogenetics. So first of all, as I hope to have conveyed, the parameter space is humongous, right? And very complicated because the branch lengths interact with the tree topology in a known standard way. And it's also very big. And importantly, these runs take days at a minimum, right? So we're not talking about things that you can do in a couple minutes in Stan. We're talking about things that take days to run, right? So what we need is early stopping. So this is something that's an idea that I would like to put out there, that we need to think about SBC in sort of a step-by-step way, whereas you do a few simulations and you try to detect gross problems so you can stop early and not waste a lot of computation power to discover in the end that your sampler is bad and your model is not well calibrated for that sampler. The other difficulty that I would like to mention is that because the parameter space is very non-standard, there's no way to do a single proposal that updates all of the parameters at once, as you do in Stan, right? So in Stan, what you do is you write down your model, Stan maps that to Rn, does HMC in there, and then maps back, right? That cannot be done in phylogenetics, at least not easily. So what we usually do is we have a set of proposals for omega, we have a set of proposals for T and for B, for the tree topology and branch lengths. And having multiple proposals means there are other knobs that you need to turn in order to calibrate your sampler, right? So there's no, in Stan, if Stan works, then it works, right? Because it has a single proposal. But if in other phylogenetic software, if it doesn't work, you can never know if it's because one of the proposals is messed up or because something else deeper, some deeper problem is at play here. So I hope to have conveyed these special features of phylogenetics and probably give you food for thought. So with that, thank you very much. I'll see you in the live Q&A session. Bye.
Thanks for the talk. Our first question is from Martin. It says, would there be a reason to not compute a large number of different distances for your tree SBC?
Thanks, Martin. That's a good question. No, you can compute a bunch of distances, and we actually do that. What I can say, well, my answer is going to be multi-parted. So the first thing is BHV distance, for instance, is a very good metric because it takes both branch lengths and branching order into account, and there are deep mathematical motivations for its utilization. So, so for instance, people have used BHV space to do HMC in, right? So it's a very good metric to compute. But if you have a tree with thousands of leaves, which is not uncommon, especially not during COVID, it's going to be a bit hard to compute. But yes, computing this distances is usually not the bottleneck, not the computational bottleneck in this framework. But I'm going to answer a question that you didn't ask, which is, or make a comment about the fact that if you have different distances, but these are telling you different things, so one of them is flagging problems, but the others aren't, I find that difficult to deal with. But you can always take a very conservative approach, which is compute a bunch of distances, and if any of them flag problems, then you investigate those further, I suppose. Right, so that's the answer I wanted to give.
And the next question is from, sorry if I botched your name, but it's Javier Montano Chiriboga. He says, can you do the same thing with the alignments before you have any tree?
I don't know, because the usual progression, logical progression, is I generate a tree, then I generate an alignment, and then I infer approximately the posterior for both trees and omega and everything else. So if you only have the alignments, I don't know how you can fit that into a generative framework where, first you have to have a tree that underlies that alignment. There are other things that you can do if you just have the alignment and you want to do, prior predictive checks or stuff like that. But in this particular framework, I don't see how to incorporate the fact that you have alignments without trees. But feel free to shoot me an email and we can continue this conversation.
And I also personally have a question, and this might be a simple one because I'm not too well versed with phylogenetics. But how is the ancestry relationship constructed?
Sorry, what? How is what?
The ancestry relationship constructed. So in the tree, how are the leaves connected to each other?
Right.
Because I mentioned using gene sequences in the as data.
Yeah. So the way you relate sequence data to the tree is through a mutation model, right? So what we usually say, crazily, if you ask me, is that the individual sites in an alignment are conditionally independent given everything else in the model. And then with that, if you assume, for instance, a Markov model of mutation, so each particular state is a state each particular nucleotide is a state in that Markov chain, then you can, using, Bayes-Nett's conditional independence structure, compute the likelihood of the tree. So the likelihood of observing that particular alignment given some parameters for the mutation model. So that's how you relate a particular alignment with a particular tree. Does that answer your question?
Yeah. I see. Thanks for the answer. Okay, if there isn't any more questions, then we'll be concluding the talks, and I'll be tossing the mic back to Martin for some conclusion remarks. Once again, thanks for your presentations.
Thanks, everyone.
Okay, thanks everybody for coming. Thanks everybody for speaking. I'm glad this worked out. I hope you all get stable connection and heard everything. I'm especially thankful to people who tried the tutorial, and so we will not be closing the online space after the talks end. So you may try to chat in text or at a table with the speakers who are still there, or with the organization team, and we'll hang around for a couple more minutes unless somebody shows up. And with that, I also thank my co-organizers, Hunji and Shin, who conceived the project. I was just tagging along a bit and then did some stuff. So I'm super happy that we could make this. I hope you're gonna give the SBC package a try. I hope you're gonna file issues. I hope you'll find the work useful, and you'll be able to be more sure that your models do what you think they are doing. So have a nice day, and see you on the Stan forums or at the next StanConnect or anywhere else where they do good statistics. Bye.